So I have already uploaded the solutions for the second quiz. Okay, so let's start with today's class. So in the last class we were discussing about we were looking into some problems or trying to solve how to draw a root locus from a given open loop transfer function. Okay, so we have seen that there are certain rules or you can say that certain guidelines are there. So if you follow those guidelines and you proceed step by step, you can find out all the information that is needed in order to draw an approximate root locus. Okay, so then we also talked about what is the effect of adding poles and zeros to a given open loop transfer function. Okay, so in general, just the conclusions that addition of poles to the open loop transfer function, that is GSHS, that usually results in increasing the order of the system, because in the denominator, since the poles are added in the denominator, so that means the highest power of the denominator polynomial that increases. So that means the order of the system is higher. Also, the effect of adding poles, what it does is that it shifts the root locus to the right half of the, or it shifts the root locus to the right side, or you can say to the right side. And it might so happen that the root locus sort of reaches to the right half of the S-plane, and thus making the system unstable. Okay, so that means you can say that since the whole root locus is now moving towards the right, so that means the stability constraints are now more restricted. So initially maybe added a pole to your system, since the overall root locus that is shifting towards the right, then the value of k, or the range of k for which your system is stable, that range becomes much more constricted, and that means that the stability constraints are restricted. Also, you can say that this movement of the root locus towards the right half of the S-plane, that indicates that the damping ratio is actually decreasing. So if the damping ratio is decreasing, means that the damped frequency of oscillation that will increase. Also, the settling time, the rise time, peak time, they are also a decrease in those parameters are also observed if you add poles to the open loop transfer function. However, in the contrary, if you add zeros to your system, zeros to your open loop system, that is reflected as a decrease in the order of the system. Okay, so decrease in the order of system, because now or you can say that the root locus is now basically shifted towards the left side of the S-plane. So the moment the root locus is shifting more towards the left half of the S-plane, so that means the relative stability of my overall system is improving, because it is moving farther away from the imaginary axis, and the farther we move from the imaginary axis, the better is the relative stability of the system. Okay, and also the settling time of the response, that is faster when you have if you add zeros to your open loop transfer function. Okay, so then we look on, like, after we have drawn a root locus. So fine, after drawing, the main purpose of drawing the root locus was that we wanted to know how the closed loop poles of the system, or where the closed loop poles of the system will lie for a given value of the system parameter. So the system parameter that we usually consider is the gain of the system. Okay, so our main concern was that given the open loop pole and zero information, so given the open loop transfer function, from that how we can find out what will be the location, or what will be the path of the closed loop poles and zeros of the system if we change the overall system gain. So that was the main idea of drawing the root locus. Okay, so once you have drawn the root locus, then you can say you can find different parameters from the root locus. Okay, so let's say that if you have to achieve a desired speed of the response, so the moment you have to achieve a desired speed of the response, so that means the time constant of the system that will be specified. Okay, so and the time constant is specified, it means that the or rather you can say that the overall speed of the response, that is determined by the largest time constant. And the largest time constant is equivalently, you can say that the slowest component of the overall system, that basically guides what will be that governs what will be the speed of the speed of the response. Okay, so that means you can say that the speed of the response is determined by the largest time constant, or in other terms you can write this is the slowest component of the system. That is appearing in the characteristic equation. Okay, so now on the root locus plot, if you the lines which are parallel to the imaginary axis, they have this constant, they are the lines which have constant 1 by tau value. Okay, or you can say that these are the constant zeta omega n terms. Okay, so if you remember that if you have a characteristic equation, the general form of the characteristic equation was s square plus, so the general form was s square plus 2 zeta omega n s plus omega n square is equals to 0. So that was the general equation of a characteristic equation, and the solution of this equation was, if you write, so this was minus zeta omega n plus minus j omega n square root of 1 minus zeta square, provided the value of zeta is less than 1. Okay. So here you see that, so that means these are the poles of my closed loop system, and the real part of the poles is this minus zeta omega, and this value is the real part of the pole, and the imaginary part of the pole is given by omega n square root of 1 minus zeta square. So you can say that if your the line which is parallel to the imaginary axis at a point zeta omega n, so they will be, so at all of these points, the value of the real part remains constant, the value of the imaginary part is changing depending on where on the line you are lying. So you can say that on the root locus plot, if you draw lines which are parallel to the imaginary axis, they actually represent the lines having the constant value of 1 by tau, or you can say constant value of zeta omega n values. Okay, so the moment you, if your this tau or this zeta omega n, this value is specified in your system, so you can see at what point actually this line is actually crossing your root locus, and from that point you can find out what will be the value of omega n, the value of omega d. These things, all these other informations can be found out, the value of zeta, omega n, omega d, all of these values can be found out from the intersection point of the root locus with this constant 1 by tau line. Okay. Similarly, if you want to have a certain desired oscillatory response, okay, so your system will, if you go back to the time initially when we were talking about the time response of a second order system, we saw that if your system is an underdamped system, that means that the time response or the step response of the system was oscillatory in nature, right? So it was the oscillations were damping down. So the step response of a second order system for an underdamped, so it was something like this. It was dying down with, so this is for second order system and underdamped. For that you have, so the step response look like something like this. So that means the output is an oscillatory response. So for an oscillatory response, the pole, the position of the poles that is needed for an underdamped system is a pair of complex conjugate poles. Okay, so if the poles of the closed loop poles of your system, they lie, or not the closed loop poles, sorry, if the open loop poles of your system, they are a pair of complex conjugate poles, then you can say that the system is underdamped. However, if the system, the open loop poles of your system, they lie on the only on the imaginary axis, or you can say that the closed loop poles of the overall system is lying only on the real axis, then the system is known as a overdamped system. Okay, so overdamped system, for overdamped you can write that closed loop poles on real axis. So that means there will be no oscillations in your system. And for underdamped system, the closed loop poles, you can say they should be complex poles. Okay, so in case you want the desired response that we want is an oscillatory response, so the damping characteristics of maybe the damping characteristics of the system should be specified. Okay, so if you have an oscillatory response, so that means you will need to find out what will be the value of omega n and omega d, omega n being the undamped frequency of oscillation and omega d is the damped frequency of oscillation. Now in the root locus, again, if you draw the lines which are parallel to the real axis, they correspond to the lines which are constant omega d lines. Okay, and the constant omega n values are basically the circles which are circles with the origin as the center, and the radius of that circle is given by omega n. Okay, so the lines which are parallel to the real axis, that is constant omega d line. Lines which are parallel to the imaginary axis, that is constant zeta omega n lines, and the circles with origin as the center and the radius as omega n, those circles will be constant omega n circles. Okay, and obviously the relation goes like this, that the value of omega d is equals to omega n square root of 1 minus zeta square, and 1 by tau is equals to zeta omega n, and the value of zeta is given by cos theta, where theta is nothing but the angle between the real axis and this omega n vector. Okay, and these values are obviously valid only for an underdamped system, that is the value of zeta is less than 1. So if you are given with a system where this certain let's say the time constant is specified, or maybe the value of zeta or omega n, these things are specified, or if it is given that you should have an oscillatory response. So the moment it is given that you should have an oscillatory response means you can infer that my system will be underdamped. So that means my closed loop poles will be a pair of complex conjugate poles. So you have to infer depending on what is the system specification that is given, and accordingly you have to find out what all will be the parameters, the value of gain of your system, so that the given specifications are met. Okay, so yeah, so here is one problem where it is given that the open loop the forward transfer function is given, the feedback function is also given. So you can find out what will be the value of the open loop, so the value of GS into HS, and it is given that it is desired to have a maximum time constant of 0.8 second without any oscillations in the closed loop response. Okay, so that means the value of tau is specified, tau is given as 0.8 second. So you can find out, you can easily find out what will be the value of the real part of that pole. So this will be nothing but zeta omega n. Zeta omega n will be equals to 1 by tau. Here we have seen that 1 by tau is equals to zeta omega n. So you can find out what will be so for this time constant, the corresponding, so if the system has to have a maximum time constant of 0.8 seconds without any oscillations, that means that the roots of the characteristic equation must lie to the left of this point, right? So, and again, no oscillations means that the system will be overdamped. Overdamped means the roots, they must lie on the real axis. So you can forget about having complex conjugate poles. Okay, so given all these things, then you have to find out what will be the value of K for which this condition is satisfied. So what you need to do is that you have to find out the breakaway points, and if you remember that at breakaway point, a point is known as a breakaway point if there are multiple roots of the characteristic equation, they exist at that point. Okay, now since in this system this is a third order system, right? So that means you will have 3 closed loop poles of the system. Okay, so now the moment you find the breakaway point, so that means that 2 double roots or 2 roots will be present at that breakaway point. Okay, so you need to find out what are the value of those roots, and you also have to find out what will be the third value of the root. Okay, and why you need to find out all these roots is because given the criteria that tau should be less than equals to 0.8 second, you have to find out whether this condition is satisfied at that corresponding value of the root or not. Okay, so similarly you see whether these conditions are satisfied. If it is satisfied, then you can say that okay, for this value of k, the system specifications are satisfied and the system does not have any oscillations in the closed loop response. Okay, then what you need to do is that you have to find out that you increase the value. So you have found out some specific value of k. Okay, so in the next step, what you need to do is that you increase the value of k to to 10, and then you see that after you increase the value of k to 10, how the roots of the or the poles of the closed loop system, they are changing. So depending on the position of the new closed loop poles, because now you are this gain value has changed. So the moment the gain value has changed, so that means the position of the closed loop poles will also shift. Okay, so what you need to do is that you have to find out what will be the closed loop poles for if the gain of the system is equals to 10, and depending on the poles, the position of the poles and the corresponding time constant at those points, you have to commit on the on how the system response will be, whether it will be still overdamped or the system will go into an underdamped situation. If it is underdamped, then what will be the value of corresponding zeta, omega, and omega d? These things you have to find out. Okay, so I have already given you like I have written the process of finding out of solving the problem. I have just not done it mathematically. So you can try solving this later on at your home. Okay, so then we will talk. So this is very important. This is important in the sense because if you look from a practical point of view, so a practical point of view means that whenever a system or an engineer or a designer is trying to develop a control system, so he or she, they know what will be the desired response that is needed for my system. Okay, so depending on the desired response or the nature of the desired response, you have to change or you have to specify or you have to design your control system in such a way that you have to adjust the values of the poles and zeros, you have to adjust the value of the gain, and if you have some other parameters, you have to adjust everything according to the given system specification. So you need to find out, you need to understand the correlation between the given specifications related to the output of your system to the system parameters like oscillations or the this damping, and where the depending on the root locus, how you can find out which point corresponds to the specifications that have been provided. Is it clear?
Yes.
Okay. So next we will see, so till now we have seen that how to draw the root locus of a system which doesn't involve any lag or a dead time. Okay, so now if you have been given with a system which has an inherent transportation lag, okay, so the transportation lag or a dead time. So that means in the previous systems what we had is that the moment you are applying the input, that input is getting reflected as a change in the output. So there is no delay between the position or the time at which the input is applied and the time at which the output is getting generated. Okay, so they are instantaneous. So, but now if you have been given with a system which has a transportation lag, so that means that after you have provided the input, it takes certain time. There is a certain delay which is involved before the output gets generated. So those kinds of a system. So now we will see that how to draw the root locus for those kinds of a system which is involving transportation lags. Okay, so if you write the open loop transfer function of a system with transportation delay, that is given by k into e to the power minus st. So this e to the power st, basically this is the term which corresponds to the transportation delay. Okay, so you can write, for if the value of t is very small, that is the delay which is introduced, delay which is present, that is a very small quantity, then you can expand, if you write the expanded form of e to the power minus st. So e to the power minus st is equals to 1 minus st plus s square by 2 factorial t square, and so on and so forth. Now, if the value of t is very small, what you can say is that you can ignore these higher order terms. So the t square term will be even smaller, t cube will be even more smaller. So you can simply ignore the higher order terms and you can approximate this equation e to the power minus st as 1 minus st. Okay, so the moment you approximate this e to the power s minus st as 1 minus st, so what we will do is that we will just substitute that value. So k into 1 minus st divided by s into s plus 2. Now, if the value of, let's say, the value of t is equals to 1, so in that case, we can write that it will be minus k into s minus 1 divided by s into s plus 2. Okay, so here you see that the poles, they are lying on the left half of the S-plane, right? So one pole is at origin and the other pole is at minus 2. But if you see the position of the 0, for a system with a transportation delay, the position of the 0 is actually lying on the right half of the S-plane. It is lying at plus 1. It is no longer in the left half of the S-plane. Okay, so if you write the characteristic equation, so the characteristic equation we know it is 1 plus gs into hs is equals to 0. So we can simply substitute the value of gs hs and it will give you 1 minus k into s minus 1 divided by s into s plus 2 equals to 0. So this is your characteristic equation. Now, for drawing the root locus, we will follow all the rules which were valid for which we have seen for for the previous case, for the systems which do not involve any kind of delay. But there are two conditions which are modified while drawing the root locus of systems with delays. So the first condition which needs to be modified is that the angle condition. So initially, if the system did not have any delay, so for systems with no delay, so the angle condition was if the value of k was greater than equals to 0, so angle of GSHS should be equals to 2q plus 1 into pi by, so it was 2q plus 1 into pi. So for k greater than equals to 0. But this angle criteria now will be changed for if your system has transportation lag. So the modified condition becomes angle of GSHS is equals to 2q pi for k greater than equals to 0. Similarly, for k less than equals to 0, the angle of GSHS would be equals to 2q plus 1 into pi for k less than equals to 0. Okay, so this is one condition which needs to be modified in order to draw the root locus for systems with transportation lag. And the other condition which needs to be altered is that initially we have seen that the root locus on the real axis, it existed. So for systems without delay, so the root locus on the real axis existed if the sum of the real poles and zeros to the right side of the said region is odd, right? But here the criteria is just the opposite. So if the sum of the real poles and zeros to the right of the region is even, then we'll say that the system, that part of the of the real axis is a portion of the root locus, or in other terms that the root locus exists on the real axis if towards the right of that you have even number of real poles and zeros. Apart from these two conditions, all the other rules remain the same, and following those rules you can simply draw what will be the root locus of this system. So here you see that if you follow this condition that the root locus will exist if the sum of poles and zeros on the right side is even. So you see that you have one pole over here, one pole at -2 and 1 0 at +1. Okay, so if you consider this portion between 0 and -2, so this is 0, between 0 and -2, on the right side of it you have even number of, so you have two poles, real poles and 0, so that means the root locus will exist in this portion. However, between 0 and 1, this portion on the right side of it you have 1, that is odd number of poles and real poles and zeros, so that means in this region the root locus will not exist. Similarly, if you take the region beyond this one, so beyond this one there are no poles and zeros, so you can say that that is an odd number, so there will be root locus on the real axis on the right side. And similarly for this, for -2 to minus infinity, for this region towards the right you have 1, 2, 3, so odd number of poles and zeros. So that means no root locus will exist on the left side. So you can say that the root locus will exist between 0 and -2 and 1 and plus infinity. Okay, so that if there is a root locus here, so that means the root locus will start from these two poles. They will start from these two poles and move towards each other. They will intersect at some point. So this will be the breakaway point. This is your breakaway point. So you can find the breakaway point by making this dk ds equals to 0. So from here you can find the breakaway point. Okay, so once you have found out the breakaway point, then this is the point at which the root locus is actually intersecting the imaginary axis. So this point you can find out from the Routh-Hurwitz criteria. You can find out what will be the value of k as well as what is the value of omega at this point from the Routh-Hurwitz criteria. Okay, so this point is known, this point is known, and while you are finding out this breakaway point, you will see that there are two valid. So there is one breakaway point over here and there is one. So this will be your break-in point. Okay, so that means you can say that the root locus after meeting over here, which were starting from these two poles, they will move away from each other. They will follow a circular path. They will break in again on the real axis as this point, and after breaking in, one part of the root locus will move towards this finite 0 and the other part will move towards the infinite 0 towards the right side. So this will be the overall root locus of this system with the transportation lag. Okay, so then we'll see something which is known as the sensitivity of the roots of the characteristic equation. So I want to stress on this point again, that the roots of the characteristic equation, just keep this in mind, that roots of the characteristic equation are same as the closed loop poles. Okay, so the sensitivity of the roots, so because for a system to be stable, so the roots of the characteristic equation or the closed loop poles, they should lie on the left half of the S-plane. Okay, so that means the roots will be S equals to minus, let's say, RK. Okay. So now the sensitivity of the roots to variations in the parameter k, that is given by this equation. Okay, so S minus Rk by k, that is given by variation or difference in the deviation in the position of the root divided by the deviation in the variation in the parameter k. So, in other words, you can say that in order to keep the system dynamic or system response unaffected by the parameter changes, ideally what we want is that if we change the value of the parameter, only the position of the closed loop poles and zeros should change. Okay, so then if we want the response of the system to be according to the specific value that is given, the system should be designed such that the roots of the characteristic equation, or rather you can say that the value of the dominant roots, they should be insensitive to parameter variations. Okay, so that means the value of this Sk, the sensitivity of the roots, that should be within a specified or desired value. Okay, so and why we are saying dominant root? Because if you remember that when we were talking about dominant poles, so that means that the response of the systems, that is governed by the position of the dominant root or the dominant pole. So that means what we want, if a pole is not so dominant, means the pole is lying way away from the imaginary axis. So that means the effect of that pole on the system response, that is very less. But the pole which is lying very close, or the pole which is closest to the imaginary axis, which is known as the dominant pole, that dominant pole, basically the effect of that dominant pole on your system response, that is the maximum. So obviously we would want that the dominant roots, they should be, the position of the dominant roots, that should be insensitive to any kind of parameter variation, or even if it is changing, it should lie within a specified value. Okay, so let us say that if you are given with a characteristic equation like 1 plus k into s plus z into s plus p. Okay, so that means, so here you have, so the parameters of interest here is that the gain k, the 0 position, which is at s equals to minus z, and the position of the pole s equals to minus p. So you can see that if you change any of these three values, either the value of k, minus z or minus p, any change of these parameters, that will result in a shift in the roots of the characteristic equation. So if you change k, minus z and minus p, your characteristic equation will change. And the moment the characteristic equation changes, so that means the roots of the equation will also shift. Okay. So now let's consider a system where the poles they lie at origin and s equals to minus 2, and the 0 it's lying at s equals to minus 3. Okay, so this will be the this is the characteristic equation of the system. Okay, so now if you draw the root locus of this system, so you will see that the root locus looks something like this. Okay, so you have two poles. So one pole is at here, s equals to 0, other pole is at s equals to minus 2. You have 1 0 at s equals to minus 3 and another 0 at infinity. Okay, so that means from these two poles, the root locus, they are starting from these two poles, they are moving towards each other, and this part of the and this portion of the real axis is a part of the root locus. Similarly, from minus 3 to minus infinity, this part of the root of the real axis is also a part of the root locus. Okay, so that means you can say that even without finding out what will be the exact values, so you can just intuitively you can say that the root locus, they will start from these two poles, move towards each other, they will meet at certain point, they will break away, they will follow a certain path. In this case, this is a circular path. They will follow a certain path and they will again meet on the real axis, which is a breakaway point. Once they meet at the breakaway point, one will move towards this finite 0 and the other will move towards the infinite 0. Okay, so now let's say, so once you have found out, you have drawn this root locus, so you see that the breakaway point is minus 1.27 and the break-in point is minus 4.73. Okay, so let's say that, and you see that for these values, so starting from, if whatever is the value of k over here, let's say if that is k dash, and the value of k over here, if that is k double dash. So if the value of k lies between so k lies between k dashed and k double dashed, for this condition, the closed loop poles of the system will be complex roots, because it is not lying on the root locus is somewhere not on the real axis. So that means the roots are complex conjugate roots. Okay, so this implies that you have complex, for this condition you have complex conjugate roots of the characteristic equation. Okay, so now let's say that we assume that for we take a value of k equals to 4. Okay, and for that value of k equals to 4, the corresponding complex roots are s equals to minus 3 plus minus j 1.73. Okay, so once you know the value of k, you can simply from this, either from the root locus you can find out what will be the value of the poles, or you can simply solve this characteristic equation and find out the roots. Okay, so after putting the value of k equals to 4, you see that the complex roots are at minus 3 plus minus j 1.73. Okay, so now let's assume that there are certain changes in the value of k. Okay, so the value of k is changing due to some reason. Okay, so then the value of k is changing such that let us assume that the root, this complex root, that is also shifting. So the new value of the root is, let's say it is given by s equals to minus 3.3 plus minus j 1.7. So the moment the root has shifted to this position, what you can find out is that, if you remember the sensitivity, the equation of the sensitivity was the change in the difference between the root, the previous root and the new root, divided by the variation in the gain. Okay, so from here you can find out what will be the value of delta of minus rk. So that is minus 3. So this is the new value minus the old value. Okay, so you can write, so this is minus 0.3 minus j 0.03. And you can find out what will be the value of k when s at this new position. So at this value, what is the value of k? So this is the k at this root is 4.84. Okay, so that means that the change in, if the root shifted by this amount, then the change in k is 0.84. Okay, so you can simply find out what will be the value of delta k by k and just put these values in your in the equation, and you will find that the sensitivity of the root to some positive changes, so this is a positive value, so some positive changes in k, that is given by this complex number. Okay, similarly do some negative changes in k. Negative changes in k means we are reducing the value of k from the nominal value. Okay, so for that, let's say for that corresponding condition, the root or the root of the characteristic equation, that is shifting to minus 2.7 plus j 1.7. So similarly you can find out what will be the change in the root position. Okay, so now this k is basically 3.46, so this value of delta k will be 0.54 and delta k by k is this one. So if you write the value of write the sensitivity, so this is for k minus, because we are reducing the value of k, so this will be the equation, or this will be the value or the magnitude or and the angle of the sensitivity of the roots of the closed loop, roots of the characteristic equation or the closed loop poles, if there is a change in the value of k. Okay, so if you observe that if the value of delta k by k that decreases, this sensitivity for k positive and sensitivity for k negative, both of them, they approach to the same magnitude and they are 180 degree. They have a phase difference of 180 degree. Okay, and you can say that for very small values of k, so in other terms you can write that the magnitude of these two sensitivities will be equal and the angle of sensitivity for positive changes in k is equals to minus 180 degree plus the angle of sensitivity for negative changes in k. So usually the root sensitivity is measured for very small changes. So if you want to find out the overall sensitivity, you don't need to measure or you don't need to calculate both the sensitivity changes, that is for positive changes in k and negative changes in k. You can just find only one value. So since delta k by k is very small, so if you find out only this value, you can figure out simply using these two equations, you can simply figure out what will be the value of this, of the sensitivity for negative changes in k. Okay, so that means that so the sensitivity of the root position or the closed loop pole position by depending on a certain change in the value of k, that can be determined by these equations, and ideally we would want that this sensitivity should be as low as possible. So we would not want that once we have fixed the position of the poles and zeros of the system, of the closed loop system for a particular value of k, if due to some external reason, not intentionally, due to some external unintentional reason there is a slight change in k, ideally we would want that change in k will not reflect in majorly or not reflect in a large way on the position of the closed loop poles of my system. Okay, so this value s minus rk to positive changes or s minus rk to negative changes should be as small as possible. So yeah, so this is all about the time response of a system. So we have talked about how we have seen what will be the, like starting from the initial classes, we have seen that how we have talked about different types of test signals which are generally used in order to study the output response of a system using in time domain. Then we have seen how to find out what is the how to find out information about the stability of the system. So the stability of a system, if you want to find out the information in terms of absolute stability, we would use the Routh-Hurwitz criteria. But using Routh-Hurwitz criteria, we have seen that it's not possible. It is possible to have some information on relative stability, but that information is it's a time-consuming process. So then we have moved on to root locus. So where in root locus we have seen that we could see what is the, using root locus, how we can find out what will be the closed loop poles and zeros of my of the closed loop system, how they will be affected or how they can be manipulated by changing a certain value of the gain of the system. Okay, so from there we can find out what will be the we can find out the criteria about the relative stability of the system, or how for different given specification or some given desired performance of the system or the output, depending on the output of the system, what should be the corresponding value of gain, or the what should be the position of the closed loop poles and zeros in order to get that get the desired performance. Okay. So these are all about the time domain analysis or the time response of a control system, be it a first order system, be it a second order system, or even a higher order system. So these are the topics, or these are some of the important topics on the time response of a system. Okay, so next what we'll do is that we'll move on to something which is known as the state variable analysis, or state variable or the design of a system using a state variable method. So if you remember that at the beginning of this course, initially we were talking about modeling of system. Okay, so we have seen that there are three types of three different ways to model a system. So one way was using differential equation. So if you are given with a system, you can simply write the differential equation. So that is one way of representing the system. Then the other way of representing the system was using this Laplace transform in form of a transfer function. So in form of a transfer function means you have to take the Laplace transform of the differential equations, and then you write the equation like input to the output, the ratio of output to input in terms of in the S domain, and then you find out what is the value of the. So that was another way of representing a system. And then the third type of system representation was something which is known as, which was called state space representation. Okay, so basically now we'll talk a little bit about state space representation of a system. So mainly this state space representation, that is more important when we are talking about modern control systems. Okay, so in case of a conventional control system, actually we or in case of conventional control theory, we are mostly interested in talking or in dealing with systems which are linear time invariant system and which are single input, single output kind of a system. Okay, so but the moment you move away from the conventional system, or if you come to the practical life, so then obviously a big control system that might consist of multiple inputs and multiple outputs. So then the conventional control, so that is different from the conventional control system. Okay, so that is known as the modern control theory. So in general, you can say that this modern control system will have, in order to have multiple due to the requirement of complex tasks or complex desired performance, good accuracy and all this. So there is a need that the complexity of the overall system will be more compared to a simple linear time invariant single input, single output system. Okay, so this in case of those complicated systems, so they might be multiple input, multiple output kind of a system. So the systems can be linear, they can be non-linear, they can be time varying, they can be time invariant, depending on what is the criteria that is given and what is your end goal. Depending on that, there can be different types of your system. Okay, so in case of modern control theory, what happens is that since the complication of the system or the complexity of the system is much higher than the conventional control theory, so if you follow the steps of if you just try to write the differential equations and then follow, then come up with the transfer function and all, that becomes a little bit tedious process in case while we are dealing with multiple input, multiple output systems. Okay, so for that, what we do is that we use something which is known as state space approach. Okay, so this state space approach basically in case of modern control theory. So this state space approach is also a time domain analysis, you can say. Okay, so in case of when we were talking about linear, when we talk about conventional control theory, then in those cases we'll see that later on when we'll talk about the frequency response of a system. We see that analyzing a conventional system using in the frequency domain, that is using transfer function and all, that is easier if the system has a single input and a single output. But if your system is a multiple input, multiple output system, then describing that system using a set of differential equations, which are known as state equations, that becomes much more easier. And the analysis of this multiple input MIMO systems, so that is easier if we do it in the time domain rather than moving into the frequency domain. Okay, so in other words, you can say that modern control theory basically it states that it is the description of the system equations in terms of n first order differential equations. So if you have an nth order system, then you can describe the system in terms of n first order differential equations, and this n first order differential equations, they can be combined into a single first order vector matrix differential equation. Okay, and this vector matrix notation, it basically simplifies the overall mathematical representation of the system. So, and the moment if you are increasing the number of inputs and the outputs, if you represent the system in form of the state space representation, then increasing the number of state variables or the inputs or the outputs of the system, they no longer increase the complexity of the equation. They will just increase one or two elements in your in the vectors. The overall complexity of the system or the complexity of the analysis will not increase if we are using the state space approach for representing that kind of a complex system. Okay, so now we'll see what are actually state or state variables. Okay, so basically state of a dynamic system, it is defined as the smallest set of variables. So these variables are known as the state variables, and the state variables is such that if you have knowledge of these state variables at time t equals to t0, and also if you know the input for time t greater than equals to t0, these two information that is sufficient to completely determine the behavior or the output of the system at any time t greater than equals to 0. So if this condition is satisfied, then that is known as the state. Okay, so that means the state of a dynamic system is the smallest state of variables, that is state variables, such that information of these state variables at time t equals to t0 along with the information about the input for time t greater than equals to t0, that is sufficient to completely determine the behavior of the system at any time t greater than equals to t0. Okay, so now this concept of state is basically applicable to any kind of system. It is not necessarily that the concept of state is applicable only for a physical or an electrical or an electronic system. Okay, so it can be applicable to, it is applicable to biological system, to economic system, social system, so on and so forth. But so the state variables, they are defined as the variables making up or consisting of the minimal or the smallest set of variables which can describe the dynamics of a linear system. So all these equations, all these texts or definitions will be clear once I give you an example. But just before going into the example, I just want to give you the definitions. So if you have, let's say, n state variables, that is, let's say the state variables are given as x1, x2 till xn. So if n variables are needed to fully describe the behavior of the dynamic systems, then we will say that these n variables are called the state variables, and this value of n is the minimum value. Okay, so it might so happen that you can have like 3 variables, which using 3 variables also you can represent the system. Using 2 variables also you can represent the behavior of the system. But if you have like that, then the minimum amount or the minimum number of variables that is needed in order to describe the system behavior properly, that is known as the number of state variables. And the initial state of the system means, let us, if we consider the initial state at t equals to t0, so that means the values of these state variables x1, x2 at t0, that is known as the initial state of the system. So in other words, you can say that once the inputs for the time t greater than equals to are specified, and you have knowledge about this initial state of the system, you can predict what will be the future behavior of the system. And one thing, another thing is that the state variables, this x1 to x2, these state variables are not always physically measurable or observable quantities. You can have some state variables which you can assign a state variable which is not physically measurable also. So if you have a circuit consisting of resistance, capacitance and inductance, so mostly what we do is that we either measure the voltage or we measure the current, but not necessarily that the current and the voltage only has to be the state variables. So state variables can be something which is a non-observable or a non-measurable quantity also. Okay, so now let us consider a system. So let's say that you have a mechanical system which looks like this. So this has a mass of m. There is a force Ft which is provided, and it is some displacement is happening, and you have, this is the velocity. Okay, and we assume that there is, here we have zero friction. Okay, so for this system, what we can do is that, so my input to the system is this force Ft, and the output of my system is the displacement xt, right? Displacement xt, and this Vt is basically the velocity of this mass, which is nothing but, you can say that velocity is nothing but, this is x. No, sorry. So Vt is the velocity of this mass. Okay. So now if you write the differential equations for this system, so you can write that d of xt dt is equals to Vt, derivative of the displacement is equals to Vt, and if you write for the acceleration, so acceleration will be equals to d of Vt dt, right? So that is equals to 1 by m into f of t. Okay, since the force is equals to mass into acceleration, and if you draw the free body diagram, so you see that there is only one force over this side and there is no damping or no friction, so all the other factors are zero. So you can simply write from the free body diagram, you can write these two equations. So from the first equation, from this equation, what you can write is that if you want to find out what will be the value of Vt, so Vt will be nothing but 1 by m integration of minus infinity to t Ft dt. Okay, so this, in other words, you can write this is equals to minus infinity to t0 Ft dt plus 1 by m integral t0 to t Ft dt. Okay, so this is nothing but, so this first term is basically the value of V at till point t0. So you can write this first term can be written as V at t0 plus you have 1 by m integral t0 to t Ft dt. Right, so this is one thing that you have. Okay, and in the second case, when you have the value of xt, so the value of xt is nothing but integral minus infinity to t Vt dt, right? So similarly you can write, so this is minus infinity to t0 V of t dt plus t0 to t Vt dt. So this is nothing, so this first part is nothing but x at t0 plus this part, what we'll do is that we'll simply substitute the value of Vt which we got from here. So we'll substitute this value. So this is equal to, we have V of T0 plus 1 by M integral of T0 to T Ft dt. Okay, so or if you do the this thing dt over here, so that means you can write x of T0 plus for this term, so this will be T minus T0 into V of T0 plus you will have 1 by M, you have this double integral, so T0 to T d tau and integral T0 to T Ft dt. Okay, so from here you see that this xt, so this output variable output is my xt, so this xt can be computed if we know the value of x at T0, value of V at T0 and the value of this input from for T greater than equals to T0. Okay, so that means that if we know the initial conditions, so the initial condition in this case is x of T0 and V of T0. These two are the initial condition and the input to the system is Ft. So if we know the value of Ft for T greater than equals to T0, which is this part. So if we know these three things, then we can easily find out what will be the value of this xt at any time T greater than equals to T0. Okay, so then we will say that the state of the system at any time T, the state variables. So from here we can say that the state variables are xt and Vt. Because if you have knowledge about this xt and Vt, and if you know the information about your input, then you can easily describe what will be the output of your system, or you can easily describe the dynamics of your system for any time T greater than equals to T0, which is same as the, so or rather in general terms you can say that if you have n state variables, so if n state variables are needed to completely describe the behavior of the system, then these n state variables can be considered as n components of a vector x. Okay, so maybe I'll stop right now and we'll continue talking about this in the next class. So the concept of the abstract concept of this state, is that clear to you? Like what will be the state variables? We will discuss in more details about how we can find out the state variables, or from a given system how to select like which variables will be my state variables. Those things will come later. I will discuss in tomorrow's class, but just the basic concept of what a state is or what is a state variable. Is that clear to you?
Yes, ma'am.
Okay, fine. Then that's all for today, and we'll again have our next class tomorrow. Thank you, everyone.
Thank you, ma'am.